So, good morning. Today I wanted to speak about thermostates and barostates, which is very important if we want to study systems where we control not only volume and energy, as is the case in simple molecular dynamics, but to describe experimental situations. Often we want to control pressure instead of volume and the temperature. So everybody knows how it is done in daily life. You have thermostats, you have just to measure the temperature and adjust it accordingly. This is becoming important in Germany now. It's a temperature control of a radiator or a climate system here. If you want to control pressure, you measure the pressure and then adjust it somehow according to the desired pressure. So here you see it a bit more precisely. If you want to, for example, adjust the pressure, you slightly change the volume until you reach the pressure you want, or for the temperature, you somehow heat your system or cool it, and then you get the temperature you want. The first question we have to answer is, how can we determine the pressure or the temperature in molecular dynamics? I mean, there is no barometer or thermometer on the computer, or the thermometer on the computer does not help. So how do we do it? For this, I will go through a simple calculation. Perhaps some of you know it's using this magic virial, which sometimes appears. And the calculation is pretty simple. There are tutorials in YouTube which explain it much more in detail. It takes about an hour, but I think 5 minutes or 10 minutes are sufficient. So we consider a time derivative of a quantity product of all the coordinates with their time derivatives, their velocities. This we can do. I mean, these are the coordinates of all the atoms. These are the velocities. This is information we have. And formally, you all know how to form this derivative, product rule. So you get dx dt squared plus xi d2xi dt squared. We multiply this by the mass of particle I. And we sum over all atoms I. So we find here sum I mi ddt of this bracket here equals, I guess you already see what it becomes. So let's first look at the right side. This is the velocity of particle I, and mass times velocity squared is the kinetic energy, twice the kinetic energy. And the other term, what's that? mass times, this is the acceleration, mass times acceleration. Oh, I missed the xi here, sorry. So these are mass times acceleration, these are the forces. Acting on particle I. Next step is now that we take the average over an ensemble. This means we repeat the calculation many times and average over all the different runs. Normally it's even not necessary to take this ensemble average. There's a very deep statement that ensemble averages equal time averages. So if you let your system, your molecular dynamics simulation run for sufficient time, it's equivalent to take 10 runs and average over 10 runs or so. Yeah. This is normally denoted by such angular brackets. Sorry. So now we have a closer look to the left side. Until now, I just started with this term here. What do we know about the left side? We average over all coordinates and velocities. And a particle can move here, or can have a velocity like this, or can have a velocity like this, or like this, and can have a position here or here, and so on. So positions and velocities are not correlated. Yeah? And as we heard already in one of the former lectures, the velocities have to cancel out. Yeah? Otherwise, your whole system would move through space. This means that for every velocity, you find a velocity in the inverse direction. This means that all these terms cancel out if I take the sum and this average. So this is just 0. Perhaps I should write this here. Uncorrelated. The average velocity is 0. This term vanishes. This is already nice. The right-hand side, there's the kinetic energy and this strange average over the product of positions and forces. And since it's such a strange term, it got its own name. I think somebody already mentioned it. It's called the virial. It comes from Latin, this term, vis is a force, and it's some kind of sum over the forces. Yeah. Furthermore, we assume that it is an isolated system. Without any special external forces. So this gets abbreviation W. So we end with an equation 0, that's the left side, equals 2 times the kinetic energy average plus this virial here. Perhaps I should write again, this virial is what does it help? I mean, until here, temperature and pressure did not show up. Yeah? First, the first term here, the kinetic energy, more or less defines us the temperature. This is coming from this equipartition theorem, that per degree of freedom, on average you have 1/2 kT. So, sorry, there's an n missing if I have n particles. Each particle for each degree of freedom has 1/2 kT of thermal energy, of kinetic energy. Since we have 3 directions for them to move, we have no, or we assume that we have no vibrations inside the particles. So if you consider molecules, for example water, there are internal degrees of freedom. This we don't consider. So then the kinetic energy is just 3/2 nkt. Or other way around, this first term here gives us the temperature. So if we measure the velocities, this was what we had above here, 1/2 dxi dt. We get the temperature. So this part is comparably easy, and we used it already. In a sense, we are done during the Monte Carlo molecular dynamics simulation. We measure or we register the velocities, and we get the temperature. And by the way, this is also important. I explained these different ways, or briefly explained the different ways to do the integration. And in some algorithms, you determine the positions on one time step, and on a half time step, you determine the velocities. So you don't have the velocities precisely at the same instance as you have the positions. This can be perhaps a bit dangerous. The second term is a bit more difficult to understand. This is virial. What can we take out from the virial? I mean, as you already might expect, this has something to do with the pressure. Otherwise, I would not make this effort here. For this purpose, we look at a small volume. cube of side length L. It's not a perfect cube, but and we divide or we split up our forces on particle I in an external force, but this is not an external force coming from the outside like gravity or electromagnetic fields or so, but just the external force acting on the surfaces of this cube. So there's something missing. And we have the internal forces caused by the interaction with other particles. And basically this external force acting on the surfaces, this is what we know as pressure. That's the part which leads to the pressure then. So if we have a pressure, acting on one of these surfaces, this means, maybe I should put a P here. This means that this external force L square is the area of this cube, and we have these forces in x direction acting at x equals 0. If we have the x-axis coordinate system, y and z. So we have here x equals 0, x equal L, y equals 0, y, no, that's z here, z equal L, and so on, yeah? It's plus minus here, sorry. So inside the cube, these surface forces are 0. There are only internal forces. Now we do this integration of this variable, or the summation. Over the external forces. So we have the coordinates here in the origin, which is 0 here. So fx, so this would be, how do I write it? It's just 0 here at x equals 0. We would have a force here, P L square, minus here on the other side. We have our P L square here, so this force, and we are at the position L, x equal L. Same for the y direction. And here we have again this force PL squared times L. And so this just sums up to minus 3 times P times L cube. And it's rather primitive, but L cube, of course, is the volume of our cube. That's what we need. Yeah. So this virial so this means that this equation from above here, this one here, 0 equals 2 kinetic energy plus this W. Simply becomes, let me see, oh yeah, the kinetic energy is 1/2 the velocities and so on, so it's 3 kT. Sorry, I made a mistake. This is, of course, not correct. This is just the part of the external energy. For the external forces. The internal forces gives their own contribution. I was already one step before here. So this is this part here, and we keep the virial of the internal forces, which I did not discuss further here, but this is, of course, a term we have to keep in mind here. So this is the full equation, which allows us to calculate the pressure. If we just solve it here for the pressure. So to determine the pressure, we determine the temperature, which we did before from the velocities. We needed for the calculation, for the simulation, the internal forces. This is what we discussed before. Yeah, you have all the forces from Lennard-Jones or EAM or whatever. You have the positions. So you sum up these terms here, divide by the total volume, you get the pressure. And there's a nice side remark. This is, I was a bit confused for a moment. If you have no internal forces, I guess you all know this situation for gases. We call it an ideal gas. all the internal forces are 0. And what do we get? 0 equals 3 nkt minus 3 pv, or if you bring it to one side, this is what I hope you all know from school, the ideal gas equation. Yeah? You get it for free here in this simple considerations, which also tells you that you made at least no severe mistakes in the past down there. For example, that these factors 3 cancel out. Okay, so that's how we can determine the pressure and the temperature during the simulation from all the data we obtained during the simulation. Yeah? So there's no, besides this conversion here, no extra data required. Next question, of course, now is how can we adjust the pressure and the temperature? Basically, it means that we need some computer thermostat. Yeah? We know it now. And this is a simple approach which I showed in the slide before, what you could do and what some people do. You run your simulation for a while, measure the pressure, and then if you see it deviates from the desired value, you just decrease the volume or increase the volume. Yeah. Same you could do for the temperature. It's not so obvious here. Same you could do for the temperature. You readjust the velocities to the desired value, so to get back to the temperature, to the set temperature. Yeah? But that's not the best way to do it. I will explain why. So the naive and most straightforward way is for temperature, rescale velocities every now and then. To get back to the set temperature. And same for P. You rescale the volume. To get back to the set pressure. Why do I call it a naive way? If we now look at the course of the velocities, this would mean our velocities of course they show some fluctuations about an average value. Perhaps now it deviates slightly, and then I switch on my thermostat, go back here, like this, and then I switch on again. No, sorry. Like this. Yeah? And strictly speaking, this means that the spectrum of fluctuations becomes non-physical. I have here these strong events when I just push it back. Yeah? never make a graph without naming the axis. So this is the velocities. Unphysical or even arbitrary. Depends how often you do it and so on, yeah. I will go a bit more in detail into these fluctuations. I mean, by the way, why are we interested in the fluctuations? I mean, we are happy if the equilibrium values are more or less correct, yeah? But the fluctuations, they are responsible for all, say, unexpected events. So, for example, for diffusion jumps or some other rare events, yeah. So, for example, if you drive out the system from equilibrium, how does it go back to equilibrium? It's caused by fluctuations. Yeah? There are other applications for the fluctuations, which perhaps we see here. I don't know whether. I think I mentioned it yesterday. You can also exploit the fluctuations to determine other quantities. For example, the temperature fluctuations in a real system become large if the specific heat is small. They become small if the specific heat is large. So you can use the temperature fluctuations to determine specific heat. You can use size fluctuations, volume fluctuations to determine moduli, and so on. So there's a deep relation between fluctuations and related quantities. Yeah, it's called a dissipation fluctuation theorem in statistical physics. So, believe me that fluctuations are important and that we should care to use barostats, thermostats, which do not create artifacts. And that's, I think it's a pretty common mistake if you look into literature where people apply molecular dynamic simulation. Often they use this rescaling barostat thermostat. Yeah. I mean, it's the most simple one, and often it works. I mean, I should not be too strict, yeah, but you should bear in mind that it is a bit risky. So if I look at the fluctuations in momentum, the probability for a momentum p we can use what we learned earlier. It's given by this Boltzmann factor. So the energy corresponding to a certain momentum is given by the kinetic energy, p square over 2m. It's the probability to deviate from the average momentum, and divided by kT. Since it's a probability, it should not be normalized to 1, so we have a normalization factor, which in 3D is 2 pi. It's just if you integrate over the Gaussian here. Power 3/2. So this is just a normalization. And that's the Boltzmann factor. If we have such a probability distribution, we can look at its expectation value. So expectation value for P itself is 0. I mean, fluctuations in one or the other direction, they cancel out, but the P squared is interesting. And P square, apart from this factor 1 over 2m, is the kinetic energy. How do you get an expectation value? You just integrate this probability distribution over all possibilities for P squared, and then this probability. And this integration can be done on paper or using tables or so, or perhaps using Mathematica. Becomes 3m kt. This is what we already used before, yeah? It's kinetic energy. You can also look at the expectation value for this P square squared, P4. And that's a nice thing about Gaussians. By partial integration, you can always solve this integral. And this becomes 15 times mkt squared. I'm a bit puzzled about this factor of 15. I hope it's correct. This is 4 m squared kinetic energy squared. I should check this factor of 15. So it looks a bit strange. Or you can check it, yeah. I mean, it's not so complicated. And this means now we have the expectation value for the kinetic energy, which is given by the temperature, and we have the expectation value of the square of the kinetic energy. And this allows to get the variance. So sigma of the kinetic energy takes expectation value of the squared quantity minus the square of the expectation value. Yeah. Or the relative variations, or relative variance, if you divide by the expectation value squared. Divided by the So now we can look here. This is, divide out the mass here. Mass is squared on both sides. This is 15 over 4 kT squared. This one, if we square it, becomes 9 kT squared equal 4 Ekin squared. So this is 9 over 4. Divided by this 9 over 4. And that's a very simple number which comes out. So the fluctuation should obey this relationship. That's the variance is just 2/3. And this allows you to control whether a thermostat is a good thermostat. Otherwise, you get the wrong fluctuation spectrum. And one could check with this rescaling thermostat what comes out there. You can easily do it with simulations. Here you see fluctuation spectrum of temperature here, of pressure here, and of kinetic energy for this rescaling thermostat and barostat here. And for one, which I explain in a moment, Mose-Hoover, which is considered a good one. By bare eye, here you don't see a big difference. Here for the pressure fluctuations, you already see that there are differences. I mean, here the fluctuations are stronger as they are here, and even the average value is not well hit. If you look at the spectrum or the histogram, here for this rescaling algorithm, and for this Mose-Hoover, you get this distribution. For the kinetic energy, here I mark these values. The mean value, of course, is the same because this is a set temperature, but the standard deviation here is much smaller as it is here. And other parameters, the skewness, the kurtosis, they are quite different. So the spectrum of fluctuations, I would say, is not very well met here with this rescaling thermostat. I don't know, I did not check whether this gives the right values here, but this 0.62 is 2/3 I just derived, so sounds reasonable. And I have no idea what one would expect for this skewness, probably 0. Should be 0, I guess. Symmetric. So. Yeah.
Otherwise, it is right skewed or left skewed depending on. I think that is heavily skewed.
This one here. This is.
Kurtosis is also 3 or 4. I don't remember. Some number if it is a nice Gaussian.
Okay. This I also don't know. I'm pretty sure that people checked this one here, and this is considered a good one. So, what is the idea behind these different thermostats? And how can we do better? And there's a couple of different algorithms available also in lumps, so you have a choice. Each has its particular advantages, disadvantages. One cannot say that one is the best or so. Some are more time consuming, some, which is also a kind of problem sometimes, they require certain time to adjust. Especially if you change the temperature, for example, then it's not very fast. So the first one for temperature, the Berenson. I just put the names, I omit the thermostat. Yeah? The idea is that you follow what is done experimentally. You put your system in a heat bath. What does it mean? This means that the atoms obtain small pushes from this heat bath. I mean, you don't do it via a surface as you would do it experimentally, but you do it homogeneously. That's a nice thing of a computer. So each atom once in a while gets a small push from outside so that it keeps the desired kinetic energy. And the direction, of course, is arbitrary, it's random, so you don't get a net momentum transfer. And a variation of this is the Lec-7. Here, yeah, similarly, you have your total acceleration. This is the acceleration of atom. Yeah, perhaps I should put an I here, which is given by the forces on atom I. And now you add random forces, not here only statistically, but you do it on each step. And these random forces also have to have a Gaussian distribution, otherwise you would violate these fluctuation requirements. And in order not to accelerate it too fast, you have a damping term. And this damping term, so a friction term, is what can make it tricky. If you make it too small, you get very long delays from these random forces. Yeah? So you get what is called ringing. The system slightly vibrates like a bell or so. If you make it too large, then this friction becomes too large. So these random forces, of course, have zero average. And polar Boltzmann distribution. And now this Berenson, he followed these ideas of Lec-7. But instead of using these random forces, which makes the system, I mean, these random forces have another disadvantage. It makes, normally in molecular dynamics, we have a completely deterministic system, yeah, apart from integration errors or so. Yeah, we can precisely follow what atoms do. If we introduce these random forces, and do a second run, we cannot precisely reproduce this first run. Yeah? And that's what Berenson avoids here. So you replace these random forces with a temperature-dependent friction term. again with a friction constant gamma, or damping constant, I think it's often called. So that's the way he does it. Again, with this gamma, this damping constant, which has to be determined and chosen properly. Yeah? So this is often a bit tricky. I think there's also barostat working this way. I'm not 100% sure. I think the Anderson thermostat is the same as this rescaling temperature. Yeah? So if you choose Anderson, I think it's the same as rescaling. It's a bit confusing because there's also Anderson thermostat, barostat. But then this, going back to Nose and Hoover, in this case, I'm pretty sure these are two persons, not like Leonard Jones. This is a bit more tricky. They introduce an extra equation of motion describing the evolution of the whole box. I mean, we have the equations of motion for each particle. So the acceleration of one particle is given by the forces, and this is what you integrate. And here, yeah, you have your simulation box. And also this follows such an equation of motion. Yeah? And it's a bit complicated how they introduce it. It uses Lagrangian mechanics. I'm not sure whether you ever came across it. I will briefly sketch how they do it. Are you familiar with Lagrange mechanics or not at all? Or I have no idea whether it's applied in mechanical engineering or so. I mean, it's a nice trick to treat some problems from mechanics which are difficult to solve using just standard Newton mechanics. It's equivalent to Newton mechanics. There's also something called Hamiltonian mechanics, which then goes to quantum mechanics. Here in Lagrange mechanics, you introduce a function, the Lagrange function, which depends on the positions. Here they are called generalized coordinates and the momenta. Q are the I mean, for us here, it's probably sufficient to take it as a normal coordinates and the momenta. These are also generalized momenta. The nice thing about Lagrange mechanics is that, for example, for circular motion, instead of using the x, y, z coordinates, you can use the angle as one of these generalized coordinates, and the angular momentum then as a corresponding momentum. Yeah? So that's what it makes a bit practical for certain applications. And this Lagrange function is the difference between kinetic and potential energy. And I mean, for a normal system, this is normal v squared, m over 2 v squared, and or p squared over 2m. If you use the momenta here, and the potential energy is what is caused by the binding energy also. And then we have, you can derive, like you can derive the equation of motion in Newton mechanics, you can also get equations of motion from Lagrangian mechanics. The momentum is obtained from the Lagrangian by taking the derivative with respect to the time derivative of the coordinate here, and the q dq. This is more the equation relating P and Q. And then you get the equation of motion. Which is dl dq minus ddt dl dq equals 0. It's called the Euler-Lagrange equation. I even went through a little example here, so if we go back to the simple things we know, so we call this qx and just one.
This most of the people who have done FEM would have seen.
Okay.
And we also take half mv squared and v of x and show that you recover Newton's equation from this.
This was what I was going to show here.
Okay.
Yeah. So for simple-minded people like me, we can just, where is it here? Write it down here. The kinetic energy is 1/2. Yeah. If I write it first, perhaps in the proper way, it's p square over 2m minus the potential energy so I put q to x and p, the momentum as before. And now if you write down this Euler-Lagrange equation, dl dq or in our case dx is minus du dx and the other term dl dx point, so I can replace this here by 1 over m over 2 x dot du dx is 2 x dot, no, not 2, m So if we put this in here, we get minus du dx, which is a force, minus d dt, so this 0 here. So you recover Newton's law from this Euler-Lagrange equation. So this is an excursion into Lagrangian mechanics. So what Nose did was to write down a Lagrangian for our particles. As before, plus further coordinates. And that's a nice thing, and that's why he uses Lagrangian mechanics. If you introduce further degrees of freedom, like the fluctuations of the total box, you just add further coordinates here. Yeah? Yes? I come to this in a second, yeah? I can write it here. S, the scaling parameter for the box. So we have our simulation box here. And this can become a bit larger. So if before it had a size x or L, now it becomes a size S times L. And isotropically. So the Lagrangian he uses is and if you do the scaling of the box, this also means that you rescale the coordinates. Yeah? So one always have to be in mind, switch back and forth between the real coordinates and the scaled coordinates. So if an atom is positioned at so many angstrom, so many angstrom, so many angstrom, if you scale the box, then it's S times these coordinates. Yeah? So that's why this factor of S shows up in the equations of motion, which we already have. So that's S squared R I dot squared. Oh, xi, sorry. In my manuscript, I used R for the spatial coordinate, but somehow I started here to use X, and I wanted to stay with the X. So this is the normal kinetic energy. Plus, now that's a new term. We get a fictitious mass of the box and its velocity, which adds to the other kinetic energy terms. And then there's a final term here, kt ln s. So this q fictitious. I call it fictitious because it's not necessarily the real mass of all the atoms in the box.
What is lambda?
Yeah, I forgot to note it here. It's a further parameter which I forgot what it is. None of you knows, yeah.
That would be the
not
mass sort of decide on the damping.
yeah. I have to look it up, sorry, I missed this point.
Because I would guess that if you change the box size, you would also change
I think
the
it's
pressure.
probably a kind of damping term as well, but I think in Nose-Hoover you don't have a damping term.
No. I mean the Q is like a...
This is a mass, yeah.
Mass, so it is some sort of...
Yeah. And sometimes one has to play with the box mass, yeah, if the system is too unstable or so. So I put lambda here and I look it up and tell you in the afternoon or so. And then this was a Lagrangian set up by Hoover, by Nose, and then Hoover gave the equations of motion here. Gave an alternative formulation of this algorithm. Basically, xi dot. I mean, this is trivial. This is more interesting here. These are the acceleration. They are given by the derivative of the potential energy, which depend on all positions here with respect to coordinate xi. So this is a normal term here, but minus a term xi pi here. I think this is obtained if you do the Euler-Lagrange equation here for this Lagrangian. And this psi derives from this scaling parameter. So you can write it this d ln s dt. And finally, we need an equation of motion for this psi, for this scaling parameter, psi dot 1 over the box mass and again this parameter lambda, which I missed to understand. So this parameter xi, this is a kind of damping constant. Yeah, it's a velocity of scaling divided by the scaling itself. So, yeah. This is lambda. I said the parameter which I missed to explain and to understand. So the nice thing about this Nose-Hoover thermostat is that you have very similar equations of motion as before, plus one extra equation for the scaling parameter or for the box size. Yeah? And this allows to both control the temperature and the pressure. You just have this fluctuation of the box. I think I skipped one here. Yeah? What?
Once you scroll up, he wants you to go up.
Ah, sorry.
This particular Lagrangian formulation that has been done, that is half m s square xi dot square. So like this is the Lagrangian that will be used for both the thermostatic as well as the barostat.
Yes.
The same Lagrangian.
I mean, because you changed also the kinetic energy by this scaling, yeah? And there's a extension of this idea. I mean, the basic idea of Nose was to just let the box by itself fluctuate, yeah? Which probably also reflects the physical situation. But it demands a certain restriction. This is that your fluctuations are isotropic, and that the box stays cubic if it was cubic at the beginning. And one interesting point could be to study transitions where the box, for example, think of a martensitic phase transformation, yeah, where the unit cell changes its shape. Yeah. And such shape changes, I think, would hardly occur under this Nose-Hoover algorithm. So an extension of Nose-Hoover is to allow also not only these unidirectional fluctuations, this can be easily generalized into 3 directions. So cubic to tetragonal, I think, is not a big issue. Then you have 3 box masses. But Parinello and Raman, that's the next one I explain here, they also allow for shear transformations. Yeah? I'm not sure. Raman sounds like Indian. Is he?
No, it could be a Pakistani also.
Okay.
But yeah, from.
Yeah. But I don't know where he's from. So I mean, all these things were developed in the 70s, 80s. I think this is here. I think it appeared in Journal of Applied Physics in '81. Volume 52, page 7182. So if any one of you wants to check it in its original form. I don't know whether I marked the reference of Nose. Fluctuations. So this rectangular box can transform into a parallelogram or like this. And this means this transformation now, instead of having one scaling parameter, you have a scaling matrix, 3 by 3 matrix, symmetrical 3 by 3 matrix, because you don't want to have rigid body rotations. So this parameter S from Nose is replaced by a 3 by 3 matrix. H. So the coordinates then are transformed x I times xi. This has to be symmetric. And again, I mean, you get further equations of motion for the whole cell. These equations become a bit lengthy, so I don't write them down. And I think he stays with one mass for the box, yeah, which makes it then not too complicated. So I don't write down the details of this Parinello-Raman algorithm. I just wanted to make a comparison of these different algorithms here. If you look on this table for the temperature, reversibility, yeah, the correct fluctuation spectrum, computational effort, and which ensemble they describe. If you just velocity, rescale the velocities, yeah, it's not really reversible. Does not have the correct fluctuation spectrum. Computational effort is low, so this is an advantage. And I put the T here. Of course, it describes an NV ensemble. And whether this is really the temperature, what it describes, if the fluctuations are not correct, you might ask. That's why I put a question mark here. Same for this Berenson algorithm. The Nose-Hoover algorithm often is a very good compromise. Yeah? So it is reversible. It has the correct fluctuation spectrum. The computational effort is not very high. And you can have both NVT and NPT ensemble. This Anderson I skipped, and the Parinello-Raman, of course, is even more general, but the computational effort is also higher. This is for the temperature, and for the pressure, I mean, these two, they are the same here. There's an Anderson P, which also has certain advantages, but basically, yeah, I don't know, I should not have. Here the volume rescaling has its disadvantages, and the only advantage is that it is simple. Same for the Berenson, and again the Nose-Hoover. I would say the Nose-Hoover for most applications is a good compromise.
So the Parinello-Raman barostat, it is used, it is a barostating that is there. So why are you looking into the NVT ensemble? Because in NVT my pressure fluctuation is not like my volume is not changing. I'm not keeping my pressure constant. In the NVT.
Good question, I don't know.
So my question is that
Yeah.
the Parinello-Raman is a
Yeah, it's the same for the Nose-Hoover. Yeah, I mean, how you keep the volume constant in Nose-Hoover.
because the Nose-Hoover is also a barostat, but I am saying that the Parinello-Raman is only a Nose-Hoover is a barostat as well as a thermostat.
Right. And same for the Parinello-Raman.
No, but the Parinello-Raman is only a barostat, no? It is like the thermostating, it doesn't do
I think the same way, because I mean, if you change the kinetic energy, if you rescale the kinetic energies, you control the temperature as well.
No, but like here I am like rescaling the box sizes.
Yeah.
Like
I mean, Nose-Hoover is a particular case of Parallelo-Raman. You agree? I mean, if you have a 3x3 transformation matrix, one transformation matrix could be just a diagonal matrix SSS, and then you are at Nose-Hoover. Yeah?
So the way to think about this, because you are allowing box volume to fluctuate, does not mean that you are barostatic.
Does not mean that I am barostatic.
Because if you give random forces or moves to the molecule, that will also result in net changes in this thing, temporary. Right? You would have to do lots of time and then it will all cancel out probably. So in other words, you only change velocity. That will correlate to both temperature and pressure. Temperature because of the velocity distribution and pressure because that is the momentum. So it's really not separated into these two. And this is a method to get control over the.
So many like MD papers or simulation papers, we see that they write like the temperature is controlled during the Nose-Hoover thermostat and the pressure is controlled using a Ferdinand Haider.
You can do that, but you can also use the same for both. You can use Nose-Hoover for both thermo and barostatic. And you can use one Anderson.
And I don't see how you can do it in parallel. I mean, then you have, I mean, basically what you do during the simulation is you solve the standard equations of motion plus these set of extra motion, equations of motion. And if you want to control the temperature using Nose-Hoover and the volume or the box size using Parallelo-Raman, I don't know what you, which equations.
Not the volume, but only the pressure.
No, not volume. I am controlling my pressure and temperature.
You run MPT,
Yeah.
but for P and T you use different.
Yeah, but which set of equation?
Nose-Hoover is not uncommon.
Which,
Anderson and Nose-Hoover, for example. People use Anderson barostat and Nose-Hoover thermostat.
okay.
So like in,
Hmm.
so like in the labs package, I don't think the Parallelo-Raman is there. But like,
Hmm.
I have used
hmm.
Lomax. In Lomax we have the Parallelo-Raman barostat as well.
Yeah.
So there we like couple the temperature with Nose-Hoover and we couple the pressure with Parallelo-Raman.
Okay.
So I think if you are just scaling,
Hmm.
you can scale and then go to the, with the scaled velocities, whatever you can do the Nose-Hoover.
Yeah.
I think that is why it is common to see Nose-Hoover and Anderson.
I'm not sure how they do it technically.
Technically, yeah,
Yeah.
that's what I don't know.
Uh.
So, and sometimes, yeah, like the Langevin is supposed to keep this thing constant, right?
Yeah, I mean, Langevin is just
zero
to,
average,
to
right?
right.
But you have to explicitly put this thing to be zero in labs, for example, like I was showing you in that.
Yeah, in the beginning. Yeah.
So I don't know about the implementation and details, how
Mm.
it works out.
In labs for NVT, this Parallelo-Raman, for the reference, whenever they have written this NVT, example, they have given the reference of the paper.
But the implementation of Parallelo-Raman is there in labs? I doubt. I think
I
Nose-Hoover
think
is
no.
not
Hmm.
So in labs we have only
Nose-Hoover, Anderson,
Yeah, Anderson,
Ferdinand, yeah, that you can get. And you can simple rescale, that is also possible.
Hmm.
But I don't think Parallelo-Raman is there in labs.
I don't know. Hmm.
They are citing it.
Because that's a classic.
We can look it up. Yeah. I mean, I'm not sure
And
whether.
to complete the other discussion, so it says Raman is born in Hyderabad in British India. I don't
I
know
see.
whether that is the Hyderabad in current India or it is in Pakistan. That is why they are saying British India. Okay, so do it. If there is any issue, you let me know. And yesterday we were looking at 3 problems, right? I mean, we were supposed to do 3 problems, and the 3 problems were lattice parameter evaluation, the elastic moduli evaluation,
and melting point evaluation. And like Sushil mentioned, for lattice parameter, there is also a way to calculate lattice parameter at higher temperatures. At the given temperature, and then take the averages and look at, and Ferdi also mentioned the time average and ensemble average. I do not know how many of you know about this. Do you know what an ensemble is? No? Okay. So, if you want to, suppose you make a system, okay. I put some, let us say 3 atoms or molecules in a box, and recording shuru ho gaya? Okay. So you want to now get the properties. So let us say I equilibrate this, and then I measure, let us say the temperature or pressure or some other quantity, mean distance that one of the particle travels. I make a calculation. Okay. Ensemble is reproducing the same structure, same simulation, same box, okay, and you will initialize, but different initializations will be different, right? Okay. Why is this so? Because you can take a same piece of copper sample and you want to make a hardness measurement, you make different measurements or take different pieces and make the measurement, you will get an average, right. So, we are trying to do the same thing, we are trying to make copies of the same system, and this collection is called the ensemble. I take different number of them and I average. But you can also, I mean, if everything is okay and everything is working fine, then you can also think that you take one system, equilibrate it, it is going to explore all these states also. So, after equilibration, if you average over time, that should be equivalent to taking these different, right. So, typically, I mean, you think that you can time average instead of doing the ensemble average. Instead of making 10 systems, you can make 10 measurements on the equilibrated system at different times, and it is fluctuating and it is probably exploring all these. So, you will get the average. So, that is the expectation. Okay. So, that is what and we will keep talking about these averages, and you will see that most of the times we average by equilibrating the system and then measuring, like lattice parameter. The box size you will measure after it equilibrates, because at a finite temperature the box size is going to be fluctuating, it is not going to remain constant. 0 Kelvin we calculated, no issues, and Ferdi tells me that there is a LAMPS script for high temperature moduli evaluation, right, not the lattice parameter. Is there a lattice parameter evaluation also?
No, lattice parameter just they have to, in that script only they have got entity ensemble or whatever.
Okay. So, you can try doing this to evaluate lattice parameter of iron for the same system at 300 Kelvin, for example. Try to set it up as simulation, and if you are not able to, or if you are facing or running into some difficulty, come back, we will take a look at it, or we will give you a model script. So, compare against it, you will know. So, basically what you need to do is to take the temperature of this system now to 300, equilibrate, and after it equilibrates, how do we know the system has equilibrated or not? Follow the potential energy, follow the kinetic energy, and the total energy should always remain a constant, and plot this kinetic plus potential plus total energy in the same plot, and you will see that total energy remains a constant, and there is some changes that happens in the potential and kinetic energies, and then they all reach a constant value and they fluctuate. So, if you plot, the total energy will remain a constant, maybe the kinetic energy will come like this. If kinetic energy comes like this should go like this, right, because total energy has to remain a constant. And then, I mean, this is just a drawing that I am making, that is not how it looks. Okay. Now, we take different points and we take the values, for example, the box length, and we average. If you take some 3, 6, 7 points and then you add them all up, divide by 7, that will give you the average, and because you also have 7 different values, you can calculate the standard deviation, and like you are doing in an experiment, you can put an error bar to your data. Okay. And I always find that people do molecular dynamics simulations and then report numbers without error bars. Okay. No point in doing a statistical simulation if you are not giving the error bars. Okay. So, always do at least 3. Some simulations are very costly. Okay. Even when we have simulations which run for 10 days, 12 days, etc., we still try to do at least 3 minimum. Okay. Something like lattice parameter, you should do hundreds of measurements and you should get as accurate as possible. That also takes you to something else. I mean, implementation wise, we haven't talked about, we have been talking about all these parameters in barostats and thermostats, damping coefficients and so on. You should check when you run NPT, take it to 300, then at equilibration, after you think that the system has equilibrated. So, because these are energies as a function of time. Suppose if you plotted the pressure or temperature as a function of time, typically pressure we keep as 0, I mean that is atmospheric pressure. It is not really 0, but it is such a small number, 10 power minus 5, 0 is okay. So, we keep, also because we are dealing with condensed systems. In condensed systems, pressure is not going to add too much. Okay. So, you can assume that it is atmospheric pressure which is 0. So, pressure should be like this, but plot and see most of the times it is not like this, and sometimes it can be. Okay. And then what is the effect of this damping parameter? How does that change this? Okay. You cannot keep it too small, you cannot keep it too large. You can keep it too large, then it really does not serve your purpose, because I mean, and you keep it too small, then the system is not really maintaining the pressure it has to maintain properly. Okay. This is true for temperature also, but I have found that temperature fluctuations are not that bad in general. Okay. But pressure fluctuations can be really bad. So, sometimes I wonder, I mean when you say okay, this is the pressure, right, this is doing this, is this okay or not? Okay. In any case, so when you make this NPT and you take it to 300, you also check if your lattice parameter, for example, is affected by these fluctuations. Use different damping parameters. There are recommended damping parameters that you can see in the manual, you can use them, and the recommendation itself sometimes comes in a range. It says it can be either 100 to 1000 or something like that, or 10 to 1000 or something like that. So, use 10, use 100, use 1000 and look at what happens. So, in other words, I mean all of science you should do by yourself and then check, okay, that is the whole point. But experiments are costly, you cannot do, okay? I cannot give you 10 pieces of gold and then do something and so on. But simulations are so cheap, right, you just need your laptop, you can do this. So, you should do and try to experiment with it and notice what happens and why and how, and then go back and relook. So, that is get lamps working and then try these lattice parameter and yeah.
Regarding the pressure fluctuations, like one observation is that like if I keep a system size large enough, then sir, those fluctuations can actually decrease. Yes.
Okay.
So like this is something that like I have observed by working that sir, like if I keep a larger system size, more number of unit cells.
Right.
Especially sir, when I am working with like condensed phases like liquid or solids.
Right.
Then sir, like the fluctuations are much lesser.
So, typically what is the range that you see for pressure? I try to maintain it at 0. What is it that you see?
So like if I talk about an example that I had used, so my pressure that I required was 60 bar.
Okay.
So sir, that
Okay.
60 bar, that fluctuation, if I keep a small system size, that 60 is going, the fluctuation can go up to 100 also and
Okay.
20 also.
So,
But sir,
100 to 20, but when you say small, how small is the system size?
so okay, so sir, I had around
Okay. So, 30,000 atoms, it can go to 120, okay, and then you made what, 100,000?
Then I changed it to 58,000 atoms.
Okay,
By increasing the number of unit cells.
right.
And when I did this, then the fluctuations were much lesser. So like from 60 it is going to like 75 and like that. 75 like plus.
Maybe 45 years.
So the range is like the deviation is lesser.
Okay. I don't know about it, maybe it is true. Yeah.
That's why I use for my this thing. 80,000 atom or kind of.
Okay.
If it is small, 12,000.
And 80,000 brings it to what? Plus or minus 1?
That I'm not doing. But
Plus or minus 10?
That I will see, because with 12,000, it's you can get the fluctuation of 100 bar. You can.
Okay.
Sir, but this pressure fluctuation that we are getting, like I was using the perennial Raman
Parnell.
for this, and
But no Hoover also I have seen. It fluctuates like that. Yeah.
With the small system, the fluctuation I have that I am remembering is 100 bar up down.
But what is the damping parameter?
okay, sir. So like in our case, the damping parameter that I used was, so my dt was 0.002 pico, which is like 2 femtosecond aegis, and so my damping parameter was yeah, 2 picosecond.
Okay. Okay. And what is the recommended value?
So like recommended value as in, so like usually
100 to 1000 or something they say.
sir, but like that is in lamps that does
Huh.
it. But like but we were using Gromax.
Gromax, okay.
So if we keep the damping factor large, it will slow the simulation as well.
Yeah, terribly.
It will slow the simulation
Yeah.
also. So we have to be optimized.
So that is what I am telling. I mean, so at some point these simulations change from science to art. Some people know how to do, they can get. And when you write papers also, there will be reviewers who will say, oh, this can happen, and that is true, but you don't know. So some of it is just by practice or by talking to others who are doing and getting these pointers. So which we have also arrived at some conclusions like this. And I think in Europe and England, they had a group, a molecular simulations group with Alan and all these people are also part of, just to share this kind of information. Okay. So do experiments. I don't know some of the things, but I know for Hoover also, for example, this is large, and this could be orders of even few hundreds. 0 I want to maintain, it can go to some 400, minus 400 and things like that. Right.
I have a doubt that when I went with Hyderabad, I met with the Ram. So I told him that I am facing this issue. So he told me I got up to 500 bar.
Yeah. So I have seen such fluctuations also, and we have now found a way of minimizing and doing our simulations. But I think as good practices, probably it's also a good idea to share this information or put it in a place where everybody can know and we do meaningful simulations. Okay. But I still don't know why these fluctuations happen though. I mean, there are, one is the formulation, but I don't know about the implementation and what exactly happens, why it fluctuates and so on. So,
But I mean that it scales with system size is normal, isn't it?
yeah, larger the
smaller
system,
the
yeah,
variations.
yeah, yeah. But sometimes even with the damping parameters in the recommended range, it can become really high fluctuation. Yeah. There is a mic, so please do keep it, because I think they are trying to record. So if you ask questions in the mic, it will get recorded for. Okay, so one exercise is the lattice parameter. And do it at a non-zero temperature, and that will also give you some experience with the thermostats, and use the barostats also, and you can maintain pressure at 0 or you can maintain pressure at some other value. You can do this. The second one is that there is a elastic moduli script in lamps for again non-zero temperature.
When you use this script, so there is a deformation, the strain value is a 0.02 that you have to optimize it. Because in the lamps, whenever they use, they have written that. If for any temperature, whenever you are using this thing, you have to optimize the strain value. For that, we just check. I think some parameters you have to check that it is becoming constant for that strain. Then
Okay. So look up the manual also and try this example. These are very basic things that you do, and sometimes most simulations would require this. You will see that thermodynamic integration, for example, you have to equilibrate, you have to get the right lattice parameter, then you have to get some mean mean displacement or something, mean square displacement or something. So these are standard quantities that are basic, which you need for other computations. So it is better to be very thorough with this. So try to do these things. Even if you don't do the other advanced stuff, at least this much will really help you. So just to remind you, I don't think we have too much time, but we were interested in getting the melting temperature for BCC iron, and like I explained to you, the method to get it is to find out the thermodynamically where the solid and liquid coexist without any freezing or melting happening, and that is the temperature, which is the melting temperature. This is the thermodynamic definition, and that is what we are trying to do in the simulation to get it. So let me now show you the script. This is already there, probably you have seen. Let me just run through once. Okay, so there is initial crystal melt system that we are trying to set up, and it is in 3D, and we are using periodic, and units are metal, and atom style is atomic. Okay. We have not told what is the map. I think map by default is array, right? Yeah. So that is the default value. So here Sushil has named the variables. So there is a melting temperature Tm, which is 1950, and there is a variable called room temperature, which is 300, and there is some Tne, which is equal to 1100. Okay. So and then variable x dimension 14, y dimension 14, and so on. Then we make a BCC box, we orient, and now you see the orientations are slightly different. X is along 0, 0, 1, that is x is along the z direction, but the y and z are aligned along the 1, 1 directions of BCC. Okay. Now, so x is the direction where you saw the box was elongated. So the interface normal, the solid melt interface normal is the crystallographic C, but in cubic A, B, C they are the same. So it is basically one of the cube faces, that is the solid melt interface, because interfacial energy is different along different directions, it is anisotropic. If you try to make a 110 melt solid interface, its melting temperature will be different, and that is also measured, and I think the paper gives you at least for 3 different orientations what the melting temperature is. So melting temperature in a bulk system is one number that you give, but if you are looking at these single crystals and which orientation is in contact with the melt can also decide, or which orientation you are trying to melt can have different melting temperature. Okay. It could be, I think, few degrees, Sushil, in the paper we show. Yeah. So it could be few degrees different. So you can see that the orientation is no longer with ABC with along XYZ. You can orient it differently, and there is a region, and then create box, and then we have only one type of atom, but there are 3 different regions. Right. I have a box, I have first a molten region and then solid and then molten region, right, and periodic boundary condition will take care of the melt is in contact with this melt. Of course, you can have one half solid, one half melt. By periodic boundary condition, there will be another melt solid boundary at the other end. That is what Ferdi was mentioning. You generally do not see it because we do not plot it that way, but here you will clearly see that there is a solid, on either side you have the molten metal. Okay, so I think the groups are names for these regions, and we use EAM potential, and we give the neighbor information, and up to this I think it is the same as what we did. You know, you give the time step reset to 0, and then you have a fix which is ISO and Vmax is given, and a conjugate gradient minimization is done, and there are minimization parameters, and you do this undo this fix. Then you initialize the temperature. So, there is this command called velocity, and it has all, so I am assuming for all the atoms, all the 3 regions, yeah. What does 100 and this 481516 mean?
Some random seed.
Okay, seed, okay. And 100 is the temperature you are setting, okay. So, velocity will be scaled to give a temperature of 100 using this random seed. That is how you do different simulations if you want to do the same thing. For example, you do one simulation, you get some melting temperature, and you want to do, I said 3 simulations at least. How do you do the second and third simulation? Changing the random seed will change the simulation. Okay. Okay. So, now there is a thermostyle custom step temperature, and that is another fix. So, NPT is the ensemble, that is we are making a system where the number of atoms or molecules, pressure and temperature are kept a constant. You can do NVT, you can do NVE, okay. I do not see too many people doing NPE, I do not think that is common, but so you can give these different ensembles, and temperature then goes from 100 to 300, is it? That is the fix, right? And what is 2?
2 is probably the number of time steps into my dt. So like probably that should be whatever my time step is into 1000 or 100.
This 2, this is slack coefficient or something.
This damping constant.
Damping constant.
The damping constant, but once can you show the dt that you have used?
dt is 0.001, this is metal, we always use 0.001 metal. Okay. Okay, so you can look up again the manual, and we are sharing the script. So you increase the temperature, now it has come to 300, and then we are going to 300 to 500.
So, the reason is that because we have to go to the melting temperature. So, the solid region, the liquid region, the anyhow have to go above the melting point to make it a liquid, but the solid have to keep somewhere not at the room temperature, somewhere in between. Otherwise, suddenly for a coexistence, suddenly we drop down the temperature and solid is under temperature and liquid is some higher temperature. So the coexistence, getting the coexistence is the issue out there. So that's why I make it everything at 500. This velocity solid scale 500 is required. You can use or you cannot use. That's so the equal the solid will be at the 500, and rest of the after that the liquid region that I have given a 2 liquid region. So that liquid region I have grouped it. So the liquid region, then I am ramping slowly. I have ramped above the melting temperature. So
Okay. These are tricks. I mean, you start something at 300 and suddenly something at 1800, and a small simulation cell, everything will go haywire. So we are ramping temperature. Why not ramp from 0 to 500 directly? Again, with our experience, we have found that it is always better to go in smaller steps, equilibrate along the way. Otherwise, sometimes you might get results which are, sometimes really nonsensical. Okay. So we really don't know what happens, but like you would handle any experiment, it is better to do it slowly, methodically, and reach wherever you want to reach, because if you just try to do stuff, it might give random results. And probably Sushil has done by trial and error and has realized that this is what works better, right. So, then we are taking the liquid region and then equilibrating, raising its temperature, and it is going up to 1800, 2000 also.
2000.
Okay.
Above is 1810 now is the predicted melting temperature. So
Right.
I want above, so the copper is
Sir.
liquid.
Right. Yeah.
Sir, I had some queries regarding the damping coefficients that are being given.
Right. Right.
So sir, if I look at any one of the NPs, like
Yeah.
800, 802,
Huh.
the LAMPS manual is open in front of me.
Ah.
LAMPS manual says that for my P damping, it should be 1000 times the time step.
Mm-hmm.
And for my T damping, for my T damp, it should be 100 times my time step.
Right.
So sir, if I have my time step of 0.001, then sir, this portion should be actually like sir, like it should be actually 0.1 or 0.2 or so like 2 is actually 1000 times.
1000.
Sir,
Yeah.
but sir, in the
Yeah, I'll tell you why. I mean, I agree with you that this is slightly higher, but see, this is not the final state we are interested in, right. What is my aim? My aim is to take this solid and liquid, and they should be close to their melting temperature. So, I am starting from somewhere 0, 100, 200, etc. I bring it to 500, 800, 2000 and so on. So, it is not that crucial, because that is not, I mean, I am only doing it in step, I can also directly say that okay, create everything at temperature 2000, but that does not work very well. So, we are methodically ramping up the temperature, because of which I am not too worried about the statistics. Like you saw, if the damping is not okay, so you will get some spectrum, maybe that spectrum is not realistic, it is not having skewness 0 or kurtosis 3 and so on. Okay, does not matter too much for me at this point, but I have to be more careful when the simulation is run for that specific temperature at which I am starting to do calculations and measurements and so on. Okay, so that is all. So, you can, I mean, slightly you can be off and
Temperature 0.1, whatever this thing, you can keep it, but if you go to higher temperature, after hit and trial this value, then optimize the Q is the parameter that you have seen.
that also, I mean, of course, you can also find that if 2 works for you and gives you meaningful results and you are convinced that your simulation is okay, you can use, but you can, we have used also, we have used at the upper limit or even more than that, just to take the system there and then start doing the equilibration. Okay.
Sir, what about the, so if I look at the NPT command,
Hmm.
my fixed ID is 1.
Hmm.
Then I am saying that all liquid NPT, then sir, I am giving a temperature start, stop,
Hmm.
and then the coupling.
Hmm.
So then I am doing an anisotropic pressure coupling.
Hmm.
So once can you explain what is the purpose of the drag 1.0?
I think this is the pressure drag, right? I think drag is for pressure and the other one anisotro is for the,
Sir, no.
okay.
Sir, no, I mean like, so like what are the parameters 0, 0, 2.0?
0, 0 is the low, this pressure, P low, P high.
Okay.
That can be maintained with,
See, it is for temperature 2 aniso 0 0 and then 2 drag 1.0.
No, sir. Sir, like for the temperature, it is like 2000 is the start, final is 1820,
Right.
and then 2 is my T damping.
It is NPT, right? So, for both P and T you have to give the,
Also a damping parameter, they write here. The optional drag keyword will damp this oscillation, the box oscillation. Also it alters the Noose-Hoover equations. The value of 0 leaves the Noose-Hoover formalism unchanged. For non-zero value adds a drag term, the larger the value specified, the greater the damping effect.
Right.
So it's, and I also don't see where this temperature damping comes in. I mean, in the original Noose-Hoover formulation, there is no damping as far as I know.
Just a second, Freddy. Yeah. Okay, so there is temp, T start, T stop, T damp, right? And ISO or uniso are for the P start, P stop, P damp.
Sir,
Ah.
so like that is there,
Ah.
but then apart from that there is also a drag 2.0. So I wanted to know.
Huh. So what does drag do, right?
I think drag is the same as this P temp. Or
Yeah.
maybe it's an inverse or something.
Drag factor added to barostat or thermostat. 0 is no drag.
No, so sir, like here in
Below they explain this drag parameter.
so now like in your script you have mentioned like 2.0 as the drag.
This one. Which are discussed below. Huh. Some cases, for example, solids, the pressure, volume and or temperature of the system can oscillate undesirably when a Noose-Hoover barostat and thermostat applied. The optional drag keyword will damp these oscillations, although it alters the Noose-Hoover equations.
In the fluctuation that higher that is that it control. So
Okay.
getting the high fluctuation, that
Okay.
itself control.
Okay.
That's why but there is a range is there. You can should not go above that 1 to 2.0.
Okay.
Clear, sir.
Any other question? Okay. So you take a look at this script. I think it takes slightly longer to run, and to get to those equilibration and after that measuring potential energy, it will take longer. Okay. So it's I don't know about few hours maybe
Is it 3 lakhs? What?
for the simulations. For each simulation, suppose if I am at close to that temperature and I have to get the potential energy, you have to go to at least some 250 or 2.5 lakhs before you can start taking data, right? Okay. So these are large simulations, so try to run, but at least if it works for you and if you can see for one case, we also know the melting temperature in this case. I have also given the reference for the paper, and you can go close to that temperature and see if you are also getting the same potential energy curve, if you plot as a function of MD steps. Okay. And if you go through and if you still have some questions, please do come back, we will discuss. And the dump files are also there. If you are not running, you can at least take a look at the dump files. If you do not have the resource to run and if you find it difficult, just take a look at the dump files and come back if you have any questions. Okay. So I think we can stop here, and afternoon we will talk about thermodynamic integration. There again I want to do the formulation before I show you a script, because the script takes long time to run. So we really will not be able to run the script. I will only show you and I will share it with you. So those of you who want to use it can take it and use. But the formulation at least we will discuss and understand where it comes from and how these simulations are done. Okay.